All right, in that previous example, we had the indeterminate form 0 times infinity, which told us we couldn't use L'Hopital's rule, not until we fixed it, and we fix it by bringing one of the functions down to the bottom, all right? And like I said, it was very easy to do because we had a negative exponent. Not always going to be the case. So let's see another example where we're probably going to have to do something else to turn it into a 0 over 0 or infinity over infinity. We want to evaluate the limit, right-sided limit, as x approaches 0 from the right, of x times the natural log of x. So let's do a direct substitution again. We get a 0 times, I have the natural log of 0, which you can't do. Let's take a look at the graph over here. This is shooting down to a negative infinity. So I've got essentially a 0 times a negative infinity. Indeterminate. So what do you got to do? You got to fix it. And the way that we fix it is we're going to bring one of those things down to the bottom. So here, this is what I want you to think about. Do I have an extra room? Good. I got to bring one of these things down to the bottom, either the x down to the bottom or the natural log of x. So let's look to see which one of these is going to be easier for us to work. Limit as x goes to 0 from the right of, if I bring the x down to the bottom, I have the natural log of x over 1 over x. So there's option number 1. Okay, and then I've got option number 2 is the limit as x approaches 0 from the right, leave the x on the top, and then I have 1 over the natural log on the bottom. Here's option number 2. Well, what happens on this option number 1? Option number 1 gives us the natural log of 0, which is negative infinity, what we said before, negative infinity on the top, and then 1 divided by 0 is another infinity. So I have infinity over infinity. So yeah, that's a check for L'Hopital's rule, right? Okay. Over here on the right-hand side, I would have just directly substituting 0. I'd get a 0 on the top, and on the bottom, we already said that the natural log of 0 is going to be a negative infinity. 1 divided by negative infinity gives us a 0. So we have our two indeterminate forms, both of which are a check for L'Hopital's rule. Right? This is always going to happen. If it's 0 times infinity, then depending on which one you're going to put in the bottom, you're either going to get an infinity over infinity or 0 over 0. So let's see which one we should choose, either option 1 or option 2. Remember, L'Hopital's rule, we're going to have to take some derivatives. Which of these is going to be easier to take the derivative of the top and the bottom? Option number 1 or option number 2? Option number 1, that's real easy to take the derivative of. And this one, I'd make this as x to the negative 1. It'd be pretty easy to take the derivative of. Option number 2 here, that's super easy to take the derivative of. It's just 1. But on the bottom, you'd have to rewrite this as, let's say, the natural log of x to the negative 1 power. Use the power rule and the chain rule on that thing, and this one would not be as easy to do as this one over here. So we're going to use option number 1. Okay, so hopefully whenever you're actually having to do this, it doesn't take you this long to decide. All right, so we're going to make this, well, first of all, I'm going to be thorough about this, and this is x times the natural log of x. That looks like a limit. That's better. And rewrite it, limit, now it looks like, I don't even know. It's just a combination of natural log and limit together. We want the natural log on top over 1 over x on the bottom, which goes to an infinity over infinity. And this could be plus or minus infinity, but since it's going from the right, it's a positive infinity here for the bottom of this, which is a check for L'Hopital's rule. Bernoulli's rule. That's Bernoulli. He's throwing a fit about it. So we're going to take the derivatives of the top and the bottom. So the limit x goes to 0 from the right, 1 over x on the top, and then over here on the bottom, this is x to the negative 1, so this would be a negative x to the negative 2 power, which makes this negative 1 over x squared. Okay. Now, I don't want to direct substitute it in now because I'm going to have another indeterminate form if I do, but I think I can rearrange this at this point, fix the whole thing, right? So I am dividing by, this is a complex fraction essentially, so I'm taking the limit as x goes to 0 from the right. This is 1 over x divided by a negative 1 over x squared, which is the same thing as times the reciprocal, so 1 negative x squared over 1. Right? Okay, yes. And then I can get out my consolation column, x, and just leaves an x here, which is equal to the limit as x goes to 0 from the right of just a negative x, which is equal to negative 0, or, if you want to, just 0. Another case where 0 wins the tug of war. So another way to think of this is that, hey, this thing, we're talking about some relative growth rates, this one's stronger than this natural log. Natural log is always super, super slow here as far as its growth and stuff like that. Okay, so that concludes this particular example.